When we look up at the sky on a dark and cloudless night, we can see stars everywhere, and for the most part, they appear fairly evenly distributed throughout the universe. This is what is meant when we say that the universe is homogeneous. Sure, at times we can see the Milky Way due to our position within our own universe, but overall the stars appear much the same in every direction. And it doesn't matter where or when our vantage point is, the stars above look similar, from the wilderness of Wyoming to the outback of Australia, during any season of the year. If we study the stars, we can learn to recognize constellations. But while we can learn to recognize patterns in the stars, our universe appears much the same to us as it did to the ancients who first recorded those constellations centuries ago. This concept of the uniformity of our universe in every direction is called isotropy. The homogeneity and isotropy of the universe are complemented by the general consensus that our universe has a flat geometry. But the fact that our universe is flat does not imply that it is incapable of exhibiting curvature, as Albert Einstein taught us through his general theory of relativity. This slide provides a visual depiction of three possible types of spatial curvature. We recognize positive curvature when we look at a globe of the Earth. It's interesting to note that if we draw a triangle on a flat sheet of paper and then use a protractor to measure the three angles that are created, they add up to 180 degrees. Now, if we were to draw a line on our globe between three different cities, let's say Cheyenne, Wyoming, Sydney, Australia, and Oslo, Norway, and then we measured the angles created by those lines, we would find that the angles added up to more than 180 degrees due to the positive curvature of the Earth. And conversely, in a situation involving negative curvature, the angles would add to less than 180 degrees. While I began this video talking about space and the universe as a whole, we will also be discussing subatomic particles and string theory. Therefore, we need to focus on both the very large and the very small in order to understand the ultimate endgame. So we need to have a clear perspective of scale in the universe we inhabit. This chart is from the Department of Physics at Princeton University. Notice the person near the center of the chart, checking in at a little over 1 meter in height. Actually, your arm is about a meter in length, so most of us are closer to 2 meters tall. Most of what we observe in our day-to-day world lies near that range. If we look to the far right on the chart, we'll find the Hubble length, which is estimated at 10 to the 26th meters. This represents the size of the observable universe. Now, if we turn our attention to the far left on the chart, we see the Planck length, which is estimated to be 10 to the negative 32 centimeters, or to keep our units the same, 10 to the negative 35 meters. The Planck length is basically the smallest conceivably measurable length possible in physics. So that now that I've shown you this slide and pointed out the two extremes of scale within our universe, for the most part you can forget this slide. I just wanted to be sure you realize that we will be referring to the Planck scale and the Hubble scale at times, and realize that one is very small and the other is very large. If you forget which is which, you may have heard of the Hubble Space Telescope, and since telescopes are used to view large distances, you can remember that the Hubble length measures large distances, leaving the Planck length to describe very small distances. The writer of Hebrews in the Bible tells us that by faith we understand that the universe was created by the Word of God, so that what is seen was not made out of things that are visible. When discussing the Planck scale, we will definitely be talking about things that are not visible due to their incredibly tiny size. But for now, let's take a look at the universe on a scale that affects our day-to-day existence. Somewhere in between the tiny Planck length and the huge Hubble length, we have the world we're more familiar with, which is governed by the four fundamental forces found in nature. These four basic forces are critically important in explaining the form and function of the world we live in. I've listed them from strongest to weakest. The strong nuclear force holds quarks and gluons and therefore protons and neutrons together within the nuclei of atoms. The strong nuclear force is the force that's released during a nuclear blast. The electromagnetic force exists between electrically charged particles and can be attractive when the particles have different charges, or repulsive when particles with the same charge approach one another. The term electromagnetism comes from the fact that electrical and magnetic forces are involved simultaneously. Because of this interdependence of the electric and magnetic fields, it makes sense to consider them as a single, coherent entity, the electromagnetic force. The weak nuclear force governs the beta decay of unstable subatomic particles. And gravity, the weakest of the four forces, causes mutual attraction between large objects like the planets. It was Albert Einstein in his theory of general relativity who proposed the localized curvature of space-time around objects in space and provided insight into the nature of the gravitational force. So while our universe is flat in a general sense, it does exhibit curvature that's localized around objects in space. This table represents a brief overview of the comparative strengths of the four fundamental forces, which includes a list of the quantum particles that mediate these forces. Most people have at least heard of the term photon. We can imagine a beam of light as being composed of a stream of many photons that follow a wave-like pattern. Both light and sound travel in waves as photons. The atoms that make up everything around us are all held together by gluons, the strong force mediators. W and Z bosons are essential mediators too, but we won't focus on them at this point. As we'll soon see, gravitons are a bit unique among the four mediators. One of the ways gravitons are unique is that they have not yet been discovered experimentally. Physicists are hard at work trying to formulate a theory of quantum gravity in the hope that this will lead them to a theory of everything that unites quantum mechanics and general relativity. And a quantum mediator for the force of gravity, known as the graviton, is thought to exist by most physicists. For now, we should focus, though, on the relative strengths of the four fundamental forces. Gravity is by far the weakest, and the next slide will magnify that point. If we assign gravity an artificial strength of 1, it allows us to see just how unique gravity is when we compare it with the other three fundamental forces. As I said, gravity is by far the weakest of the four forces, and it's many orders of magnitude weaker. Don't get hung up by the fact that gravity seems strong on Earth. It seems strong because the Earth is so large and is exerting a gravitational pull on everything upon the Earth, including each one of us. But the simple act of running a comb through your hair can create enough electromagnetic force in the form of static electricity to overcome gravity and lift small pieces of paper. When you pick up a book or jump up and down, you are at least temporarily overcoming the force of gravity. There's one question that physicists have struggled with for decades, and it simply asks, why is gravity so many orders of magnitude weaker than the other three fundamental forces? This problem has been dubbed the hierarchy problem. I would suggest that the hierarchy problem is not a problem at all. Instead, it's an integral feature in God's design of the universe, which we will explore more in the next video.